Hello, everybody. Welcome to Linear Algebra. This is Chapter 1, Section 1. I just finished writing this book a little while ago. I'm excited to make YouTube videos about it. I'm also kind of nervous. Oh well, we'll see how it goes. So let's get started. First, we are going to look at systems of linear equations in this class. This is kind of like a basic building block of linear algebra that we'll see how we can use it to tackle all kinds of weird, different kinds of problems. But before we get to linear equations themselves, let's go over some notation here. So, first of all, if you haven't seen this notation in a while, this R with an extra line in it means the set of all real numbers. And you can visualize R as just like the number line. Maybe you call the variable x, and it's got all kinds of numbers like 0 and 1 and pi and I don't know, the negative square root of 2. All of those are numbers in R. R2, written like this, means the xy plane, where you have pairs of numbers. And so it includes points, like any point out here. You can have negative numbers or 0. All those things together is R2. You may have studied in another class like physics or calculus 3, XYZ space, which we call R3 because there's 3 copies of R written in these perpendicular directions here. So this has x coordinates, y coordinates, and z coordinates. And it looks like that. Now, linear algebra is not just about R2 and R3, but its real power comes from when you have a whole big lot of numbers. Like, instead of 2 or 3 numbers, you might have 10 numbers or a million numbers in your list of numbers. And that has all kinds of applications in statistics and physics and all over the place. There's big lists of numbers that you want to treat sort of like the same way you would treat a list of 2 numbers, like 5, 6, or whatever. Maybe that looks more like 6, 5. Okay, so we're going to think about Rn, where instead of just x and y, you have like x and y and a bunch of other things. But the problem is you run out of letters. So instead of calling it x and y and z and then you're out of letters, we're going to call it x1 through xn. And n might be 10 or a million or anything. So in fact, R2, instead of calling it the xy plane, in this class we're going to call it the x1, x2 plane. And R3 has x1, x2, and x3. And it means the same thing as like XYZ. Okay, so that's some notation out of the way. Here is the definition of a system of linear equations. So, yeah, it has, if it's like x1, x2 through xc, those are the variables, but you're going to have some specific coefficients, some specific a11 through arc, which are all these numbers that are getting multiplied by x everywhere. And also the constant coefficients, those need to be some specific real numbers. But the x1 through xc are your variables. So a solution of the system is a list of numbers x1 through xc that you can plug in here and makes all of the equations true. And what do I mean by making an equation true? It means like the left side is actually equal to the right side, which is what the equal sign means, right? So we want to make them true with a solution. The set of all solutions is called the solution set, and 2 systems are equivalent if they have the same solution sets. We'll look at some examples of this in a bit to see exactly what does it mean to be equivalent. But first, let's look at example 1 here. So with this system, what we want to find is a value of x1 and x2 that makes both of the equations true. That makes the left hand of the first equation equal to 3 and the left hand of the second equation equal to 0. So one way to do that is by graphing. So again, remember that we're talking about x1 and x2 here. It means basically the same thing as x and y. And a good way to like graph an equation is to get it into slope-intercept form, like y equals mx plus b. In this case, that would be like x2 equals mx1 plus b, because that we would have that instead of x and y. So maybe I can do these in colors. Let's say the first equation is purple. You can just subtract x1 from each side, and this becomes x2 equals negative x1 plus 3. So this equation has slope -1 and y-intercept 3. So it's going to contain that solution, the point 0, 3. And you could say, oh, hey, we're done. We found a solution of the first equation, but we know there's an infinite number of other points because it has slope -1. We can go out over 3 and down 3, and it should look kind of like that, maybe. Okay. And so yeah, all of these other points on the line, like 3, 0, 1, 2, etc., those are all solutions of that first purple equation. But they might not be solutions of the second one. We need to make both of them true, both equations true at the same time. So with the second equation, we can do the same thing. We could write that as x2 equals 1/2 times x1 plus 0. If you add the x1 to both sides and multiply both sides by 1/2. So now we can see this has y-intercept 0 and slope 1/2, which means if we go over 2, we're going to go up by 1 and get to this point right here. Like so. So yeah, this equation also has an infinite number of solutions, like 0, 0, and a bunch of other ones, all these other ones over here. But the one that we really care about is this one here. That's the point 2, 1. And that is the only solution of the system, because these two lines only intersect at that one point. Okay, so that's doing it by graphing. Now, of course, you can imagine that graphing doesn't work very well. First of all, it would be a huge pain in R3 to graph these equations, and graphing it in R10 or R1,000,000 or something like that would just be completely impossible. Also, this wouldn't work if you have weird numbers like irrational coefficients or ugly fractions. It would be hard to see where your things actually meet. So we're going to use Gaussian elimination. Now, on the next page, there's a description of Gaussian elimination. We're going to go into this in some detail in a minute, but now you've probably done it in another class. Let's just try to go over it in a rough way, in the way you maybe remember. So the way Gaussian elimination works is we have these two equations, and this doesn't tell you like a specific value of x1 or x2 because each equation has two variables in it. So we need to eliminate one of the variables. One way to do that is if you were to take x1 plus x2 and add that to negative x1 plus 2x2, that would give you an equation that does not have x1 in it, and it would just have x2, and you could see what is the value of x2. So let's do that. I'm going to start using the notation we're going to use a lot in this class. I'm going to say we're going to take equation 1 plus equation 2. We'll see how to add them together and replace equation 2 with that result. So we're just replacing equation 2. So equation 1, I'm just leaving it alone. It's still x1 plus x2 equals 3. Equation 2 is now going to be this x1 plus x2, that's the left-hand side of equation 1, we're adding that to what we had before, negative x1 plus 2x2. And on the other side, we're adding 3 to both sides. Let's just think really briefly about why this is okay. Why is this system equivalent to the system we started with? Well, if you had a solution of the original system, that means you have like a value of x1 and x2 that makes x1 plus x2 equal to 3. So really, we're just adding 3 to both sides of equation 2. And adding 3 is not going to change the set of solutions of that equation. So that's a quick explanation of why this is okay. Anyways, let's just simplify this a little bit here. The x1 plus negative x1 is 0x1, and then we have 3x2. Okay. Then, if you see 3x2 equals 3, you know x2 is 1, but let's just go through the steps in Gaussian elimination to learn how they work. I'm just going to take equation 2 here and do 1/3 times equation 2. So equation 1 is going to still be unchanged here. Still x1 plus x2 equals 3. But now equation 2 is going to be x2 equals 1. And now that you know that, if we were doing the substitution method, you would say, oh, let's just substitute that in there. And that's fine, but I want to get used to using the method we're going to solve that's going to help us when we have much more complicated problems, just to learn how it works. So to continue eliminating this x2, instead of just substituting, we can say, I'm going to take negative equation 2 plus equation 1, and that is going to replace equation 1. And the reason for that is we want to do negative x2 plus this x2 to make it cancel out. So that's going to be x1 plus x2 minus x2 equals 3 minus 1. And the second equation that we still want to write is still x2 equals 1. And this first equation, we can just simplify this in place. The x2 minus x2 cancels out. So that just gives you x1. And then 3 minus 1 is 2. So we still get the same solution. x1 equals 2 and x2 equals 1. The same solution we had before. So yeah, this method of Gaussian elimination is a lot more applicable to lots of other kinds of problems. And the graphing is just to get an idea for the concept.